So we need the rate of reaction in terms of S2O8. So quickly, which two experiments I can use to calculate the order for S2O8?
2 and 3.
2 and 3, yes, that can use, and 1 and 2 as well. Right. So this is the order for S2.
Sir, O1 and 2. 1 and 2.
Sir, no. 1 and 2 would be for iodide. Yes, sorry about that. Right. So rate 2. Right. So let them know using experiment 2 and 3. All right. So rate 2 over rate 1 S2O8 over S2O8. So experiment 3 is, right, we use the bigger number at the top. So we're going to use 0.15 divided by 0.075. And that would be equal to, sorry, wrong thing. So 5.6 times 10 to the minus 5 divided by 2.8 times 10 to the minus 5 is equal to 0.15 divided by 0.075. This would be 2 is equal to, all right? So the order is equal to 2 over 2, which is 1. So it is first order. All right, which, and for I2, not I2, for I minus, experiment 1 and 2 for I minus, all right. So it would be 5.6 times 10 to the minus 4 over 1.4 times 10, no. And this is equal to 0.50 divided by 0.25. This would give a 14, let me see how much that gives. 14, 28, 42, 56, 4. So order 4 over 2, which is equal to 2. So it is second order with respect to I minus and first order with respect to S2O8. So so this is the order with respect to that. So the overall order is equal to 1 plus 2, which is equal to 3. So that is the overall order of the reaction. Stop. So again, when you're calculating K, you can pick any experiment. So I'm going to pick experiment 1. So the rate for experiment 1 is 1.4 times 10 to the minus 5 divided by 0.15 times 0.25 squared. All right, to prove at this point, so this is using experiment 1. I want somebody to just calculate experiment 2 for me. So using experiment 2, it would have been 5.6 times 10 to the minus 5 divided by 0.15 times 0.50 squared. So somebody just calculate this one for me. Did you have to do everything one time? So we get for this one, we get 1.49.
Experiment 2 is also 1.49.
You get this, you get 1.49 as well for
Yes, sir.
this one,
Yes, sir.
right? All right. So for each experiment, it doesn't matter which experiment, the value of K should be the same. So that is why I said you can just plug it in for a second one quickly to just to be sure that your answer is correct and you don't make any mistake. Just do it for 2 experiments. Once it is the same, then you can be sure that your answer is correct. All right, so remember for rate is equal to K S2O8 times I minus squared. So I'm just going to plug these values into the equation. So we know that K is 1.49 times 10 to the minus 3 times 0.13 times 0.32 squared. All right, somebody can just work this quickly. .98 times 10 to the minus 5 are 1.98 times 10 to the minus 5. Again, the unit for rates, it will always work out to be moles per dm cube per second. All right. So this is a typical rates question where they give you the data in the table and ask you for the order of reaction with respect to each reactant, and then ask you to calculate the rate or K or both of them. All right, so take a picture. Let us do one more on rate where you do temperature and catalyst. And I show you this thing about transition and something with intermolecular force.
So we now know energetics.
Send me I will have to leave shortly, but I'm going to just send the working note, not a video. I probably have to just try and do a working note of one and post it. Alright. I'm going to work up door neighbor one and post. Yeah. All right, I'm going to clear the screen now. The rates graph, right? Not the rates graph, the factors affecting rates. Remember the graphs, so I'm just doing temperature and catalyst. Just doing temperature. Give me a second. All right. So we are to use the diagram to show the effect of temperature. So this is the Boltzmann distribution curve. So let us say this point on a graph represents the activation energy. So you draw a line from the activation energy. So this graph, if they ask you to explain the effect of temperature and rates using the Maxwell-Boltzmann distribution curve, this is what you will draw. This is the initial temperature, and T2 is when you increase the temperature. Remember, under the area under the graph represent the amount of molecules. All right, so remember, a reaction will not occur unless the molecules of the activation energy, right? So when the temperature, let us say T1 was 30 and T2 is 45. Clearly, when the temperature was shifted from 30 to 45, this area here represents the amount of particles that are able to react. All right. So the blue area was the initial amount of particles that had the activation energy at 30. When you increase the temperature to 40, more molecules now have the activation energy. All right. So we know that as temperature increase, rate of reaction increases. So that is the relationship between temperature and rate. If they ask you to state it. So as temperature increase, rate of reaction increase. If they ask you to explain it, the energy of the molecules increases. The kinetic energy. Once that happens, I'm just putting it in kind format. Energy of the molecules increase, collision increases. Once collision increase, rate is going to increase. For catalyst, so again, let us say the activation energy without the catalyst is here. Only the molecules in this area will actually react. All right, so this area without catalyst. Remember, the catalyst is going to lower the activation energy. So let us say now here is the activation energy with the catalyst. All right, so you draw a line going up. All right, so in this area with catalyst. All right, so you can see that when you add the catalyst, more molecules are able to react. All right. So the presence of a catalyst increases the rate of reaction. All right. Explanation. Catalyst provides all right, so that's that.